Hello everyone, back to the Game Engine Development Workshop series. Just as a quick recap of what we did last time, we implemented lighting and got that integrated with our map pipeline here. If I just run this, you can see we have a light down here at the origin there. And I can come in here and quickly and easily just add another light. Let's say I want this one to be blue. 0 red, 0 green, 1 blue, and there you go. So that's done. We finished lighting last time. And today what we're going to start working on, although we definitely will not be able to finish it today, is our dynamics system. So let's talk a little bit about that. So right now we have a map data framework, and this sort of includes lighting, which we did last time. Both of these systems could be way better, obviously, both like in the general sense, but also just depending on the type of game that you are interested in making, you could optimize these in different ways and just make them easier to use. But we're not going to be doing that. We're just sort of done with them for now. They're functional. They're fast enough. We're fine with that. And so this is a pretty good foundation for a game. You know, like being able to store map data that's not hard-coded in the engine is a pretty big step, just because it, as you saw here, like I can just edit this stuff and add stuff on the fly without even needing to recompile my code and just run it, and it just works. So it's a boon to development time, and yeah, it's like necessary. But we don't yet have anything that can actually move. We don't support real movement. We have a camera, you know, that sort of scrolls stuff around relative to itself, but we don't have any things that actually move within the world, and that's sort of the next big step we're going to do. So that's what I mean when I say dynamic. Um, So just to go over the roadmap just a bit more, this time, next time, we'll probably be able to finish dynamics by next time, but if not, there will be a third one. So the next 2 or 3 lectures we'll doing dynamic stuff. Then after that, for probably at least 3, we're doing hitboxes. So I've sort of separated out into a different section from dynamics, even though it is sort of intrinsically linked. But we'll also be integrating it into our map data here, so that you could specify this rectangle as being rigid so that it has a hitbox and the player can't just walk through it. And then finally, we will get to the scripting language. Okay, so let's jump in here. I'm just going to do a little bit of housekeeping. We have some constants here in our like engine core file that are useful. And today, as we're sort of iteratively developing our dynamic system, we're going to want to tweak some values. And so it's nice to have them just sort of put into constants in here rather than just hard coding the values everywhere we use them. So I'll define a few more. One is floats per quad, which of course is just floats per vertex times vertices per quad. Next is floats per dynamic vertex. So we will actually have sort of a different data format for our dynamics than we do for our the rest of our static map data stuff. So that'll be 5 for now. So we'll leave it at the same for now. Obviously, our dynamics are still going to be rectangles. So we still have floats per dynamic vertex times just 4 vertices. We're not going to be changing that. Okay, I'll leave that open because we'll be coming back. So the first thing I'm going to do is in our world folder here, I'll create another folder called dynamic. You could define this outside, just sort of like in the source folder here, like alongside world, but I like to consider this stuff as part of the world because it moves around within the world and interacts with it. Okay, so I'll go ahead and create a header and a C++ file. And just get started here. I'll go ahead and forward declare a couple stuff, a couple classes. Now let's talk about what our dynamics actually need to store. So it's something that like exists independently of the map, where with the map, like the data that is used for drawing our map, like the vertex data, is stored in these sprite group things, which are sort of like aggregate objects that store a bunch of map data all at once, just so that it can draw it all at once, so it's more efficient. For dynamics, as I said, these are sort of standalone things, like they're separate from the map data, so they're going to store their own like vertex data essentially. So we'll need a couple vec2s, one for position, one for velocity. Then we'll have a float, which just defines like the maximum magnitude that our velocity vector can achieve. And then we'll have like a local copy of our vertex data that we will update here and then sort of upload to the GPU. We'll also have, and I haven't quite decided if this is something I'll have time to like do a lot with, but I'll just go ahead and like code this in. It's not very difficult, but this idea of different states, and you could make the argument that like it would make more sense to store this kind of data in like a character class that sort of inherits from the base dynamic, but whatever, we're just putting it in here. And all this is a list of, a map of strings, so like names to sprites. So like you can have separate animations basically that are named that you can change just by giving a name. So like if you press the left mouse button, you might say change my state to attack or whatever, and that'll change the current sprite. But again, I'm not sure if I'll actually be doing anything with that. Though I think I will probably just add some simple support for like changing the state within our scripting language when we get there. And finally, we're going to store a render object. So this is something that is bad, because it means, I'll go back to the sprite group thing just quickly once again. You can see this whole thing, which stores a bunch of map data all at once, has a single render object, which is efficient. But now each dynamic that we have has its own render object. And what this means is like the overhead on the GPU, I think that's negligible. I don't know. But really, the big problem here is that we can't batch these things together. We have to draw each dynamic with a single draw call, passing in each dynamic's sort of its own render object. And that's slow. If you have, I don't know, 100 different projectiles moving around on the screen, that's going to slow your program down. 100 different draw calls just for that stuff. But luckily, this will not be the final thing. As I said, this is such a big system that we're going to be like iterating on it. But this is just here to sort of get things going so that we can see stuff actually moving around on the screen. So if that sort of scared you, good, because it means you're considering performance. But at the same time, don't worry, we will come back and fix it later. Okay, now we'll just do some constructors, boring stuff. Just taking a position, a velocity, our list of states, and our current state. And then of course I want to delete all of this, just so we don't accidentally mess something up. And then we will delete our render object when we're done. Okay, so for now we're going to have like 3 sort of big methods. The first one is going to be update, which will pass in a frame delta, which will be used for actually performing movement. The next will be draw, which, as I said, for now we'll just draw our unique render object here. And then last will be set state, which just takes in a string and attempts to set the current state to that if it exists. And then we'll just have your basic like object-oriented getters and setters for some of our other values. We'll have get pause, get vel, get speed, and we will actually be using these. I'm not just wasting time here. I have set pause and a set vel. And then one last one to get our current sprite. Get current sprite. Okay, so there is a slight issue with our setVel function here. We have the speed variable that's like the maximum magnitude we want our velocity vector to be able to have. But within our update loop, or sorry, not our update loop, our update function here, all we're going to do there is like take the current speed, multiply it by the frame delta, and then add that to our position. We're not actually doing any sort of calculations on velocity itself. So this is the only place where velocity is going to be changed. And what that means is that when it is changed, we need to make sure that it falls within the range we've defined here. And this, it can be a little bit complicated, but luckily we have this nice vector class, and we can just add sort of a simple function here that will perform the necessary calculations for us very cleanly. So we'll get the current magnitude. And if our magnitude is less than the lowest magnitude we want, we will normalize ourselves and then multiply ourselves by that low magnitude. So remember, normalize, it's sort of just, it maintains proportions for the different components for x and y, but makes the magnitude of it 1. And then low is just the magnitude we want it to have, so we get the magnitude of 1 but maintain proportions, and then scale that up to the proper value there. And we'll do a similar check for if mag is greater than high. We'll just return normalize times equals high. Otherwise, we're already in the correct range, so we'll just return ourselves. Okay. And then in our setVel function here, all we have to do is mvel.clamp from negative mspeed to mspeed. And actually, that's probably not necessary. That could probably just be 0. I'm not sure. Because magnitude is going to be positive always. It's squared, so we can just do from 0 to mspeed. And there we go. Okay, so let's come into our C++ function or file here and start writing some of these longer ones. Include dynamic. We'll do the constructor first, which is just going to be basic, just sort of copying the values into the correct spot. We have impos is that, mvel, speed, and what else do we have? We have imvertices, which I'll just set to all zeros, and then our render object, which I'll set to null pointer for now. And then in here, even though we've set our current state just sort of inherently by assigning to it the value that we take in, it's best to actually check that whatever the user's passed in is a valid state in the array. So we'll go ahead and call setState on that. And this will just throw an error if it's not valid. So we can go ahead and write that now, actually. So get an iterator. It is not equal to mstates.end. And we will set mCurrentState equal to state. Otherwise, we'll print invalid state, whatever. Now, you could use the, here, because we're not actually using the iterator beyond checking to see whether or not this exists in the map. You could just use mstates.contains, but that's a C++20 method. And some people have, like on Mac, it's actually their Xcode is using C++17, whereas on Visual Studio, it's kind of weird. It's like you set the language standard to C++ latest, at least I did. And so that actually gives us access to some newer features than they have access to. So I'll just do this because all of this is valid C++17. Okay, that's that. Next we'll do update, which is very simple. All of these are pretty simple, actually. So update, as I said, will just take our current velocity and multiply it by the frame delta, then add that to our position. And then draw, we're actually going to need a new function for, because if I go to render.draw, I need to include render first, and probably also sprite. Go to render.draw. This takes only a single render object and a vector of sprites, and we only have a single sprite because we're just drawing only ourselves, so we'll go ahead and create a new function just for that. Where is it? Here it is. Okay, find this, and this is going to be very similar to the one we already have. I'll just copy it. Just with a single sprite. Don't need any more looping. Go, and for this, the number that we're setting is just 1, because we're only drawing the one sprite. And that should be it. So we'll draw on our render object and get current sprite. Very easy. Okay, so we do have a slight problem here. Well, we have two problems actually. One is that when we're updating our position and stuff here, this just updates our sort of vec2s here. It doesn't actually update our vertex data. So that's the first problem. And second problem is that this vertex data, we don't actually have a way to send it to our render object, even though we should. We don't have that yet. So we need to do those. The first part of that is we're just going to update our local copy. So I'll have another method called update vertices, which will be private. And this will just take whatever values are currently in our position and velocity vectors and create vertex data for us. Okay. So we also need the current sprite, just because that stores the dimensions. Because what we don't want to do is store a dimension vector here and then set that initially and use that for all of our sprites, because our sprites have their own dimensions, and so if we end up having two sprites with different dimensions, then say we start with a small sprite and then we switch to a larger one, that large one would be squished into the same area that the small one is, which would not only look bad, but it would sort of violate the illusion of our like simulated pixel-based world. So every frame, when we update these, we want to get the current sprite just to make sure that we are sizing our vertices accordingly. Then we'll get the dimensions and just sort of store those for convenience. And I'll have this dimensions array, which will just make it easy for me to sort of loop over this stuff. And this may look slightly different than what we've done before, because it is a little bit different, but it's the same basic concept of counterclockwise from the bottom left corner. So this is bottom left, and I'll talk about that in just a second here. So first we'll have our XY pair, then we'll have S and T, and then finally we'll have our index. Vertices at our offset plus 0 is going to be equal to our position vector dot x plus dims at I times 2 plus 0. So this times 2 means it'll get every other one, so it'll get only the ones that use the width, which is correct because this is the x-axis. And we'll do basically the same thing here, but just change the x to y and 0 to 1 for our y position. And this will get every other y value, so only the ones that use sprite height. And what this expression does here is it makes it so that our vertex data is centered at our position vector, which is different from how our sprite groups work. Because in our sprite groups, the position vector of the tile is the bottom left corner of the tile. But for dynamics, I do it where the midpoint of what's actually being drawn on the screen is the position. And you can do this, you could change it if you wanted to do to make it the bottom left corner if that's easier to think about. I don't think it's that big of a mental hurdle, although it is different. But ultimately, doing it this way will make some of the math later on a bit easier. Just storing the center point instead of a corner. Okay, so that's our XY. Our ST will be actually the same as we're doing them already, which will just use this sort of global corner points array, which stores the regular sort of format you're used to seeing here with the zeros and ones. And then our index, for now, because we're drawing everything on its own, the index will just be 0. And this lines up with what we did in our renderer here, where we get our sprite, just a single sprite, and update that, and we're just sending one sprite. And then down the chain in our graphics render, drawing a list of textures with just one texture. The first texture is going to be bound to slot 0. So that lines up perfectly with what we said here. Okay, so that's the first big problem. I'll go ahead and just compile just to make sure I haven't forgotten anything. Messed that up. Okay, everything else is good. So that was the first problem we had, which is we've now addressed. We're actually updating the vertex data, but now we have to send it to our GPU, to our render object. So if we take a look at our render object, what we can do here, all we can do is bind and get index count. We don't have access to any of the underlying stuff, which we can get Just need to actually do it. So let's do that. Our render object. Let's create a simple getter for our vertex array. And this will not be a const reference because we are going to be modifying this. And then within our vertex array, because remember this stores this sort of stores a vertex buffer, we need to have another getter for the actual buffer. Okay, so let's see what we can do now. We can do get vertex array dot get buffer dot can still just get some stuff and bind and unbind. So that's not good enough, clearly, because we don't have any way to send data to it. But in our buffer class here, do have a function for writing data, but it's protected, so we can't access it. So we could just bring this out here, make it public, and now we can do buffer.write, and we could do the size of our vertices, and then our vertices. And this would work. However, there are two reasons this is bad. And you may have already spotted one, just because I did talk about it before when we were writing our graphics library, is that we have hard-coded this GL static draw, which basically tells to OpenGL, it's like a hint to OpenGL about how this buffer will be used. And GL static draw means very few like updates to the data, but I'm going to be reading it often. I'm going to be drawing from it often. But for our dynamic, we need something different, because clearly we're going to be writing to it, every frame. But then we're also going to be drawing it every frame. And so there is a very similar macro for that, GL dynamic draw. But we don't just want to hard code this and use this for everything, because it does, like, it can affect performance. I haven't done any specific benchmarking with it, but that's like in all the documentation it says to use the correct one. So we sort of have a couple options for how to solve this. We could take in, like to our constructor, we could take in a GL enum usage and then just store that like this, and just do that, which would work perfectly fine. I think that's like, and this is more of a preference thing, but I think that's just a bit messy, and it makes it less clear what it's actually used for, because if we're only going to be using this value in this one place, we're never modifying the value, we're not doing anything with it other than passing it to this function, and it's never going to change. So, I mean, there's no reason to store it as part of the object. It just takes up unnecessary space. But the bigger one is, I think it makes your code a lot clearer if this is actually a template parameter. And we already have a template here, but we'll just take in another GL enum called usage, and then use that down here, just like our target. And this makes it very clear what the object is, because it's like actually part of the type rather than part of the constructor. And also it doesn't take up any space, because this will just be, the compiler will generate code for this with the given parameters, and everything will be inlined. There's no member variables. So that's our one problem. Our second problem is with the actual method we're using here, GL buffer data. So let's take a look at the documentation for this quickly. Oh, that's the wrong tab. So I have GL buffer data pulled up here. And we can see here it's pretty much what we'd expect. I think we've already looked at this actually. It just takes in the target, so like which buffer slot to bind it to, the size in bytes of the array you're passing in, the actual array, and then how it's going to be used. But if we scroll down a bit and read the description, it has some very useful information. So it creates a new data store for the buffer object currently bound to target. Any pre-existing data store is deleted. The new data store is created, blah, 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 blah. That's bad. We like deleting and creating new dynamic memory every frame, which is how frequently we're going to be updating our dynamic vertex data, that's not going to fly. So this method will not work for us. What we need instead, and it might actually have a link to it. It does. It has GL get. Oh no, that's not quite it. We want GL buffer sub data. So this is very similar. It takes in the same target, an offset, size, and then a data array. So the target is exactly the same. The offset is the offset into the buffer object's data store, so the existing block of data where the data replacement will begin. So this operates on an existing one. It doesn't delete it, it just replaces the data that's already there. And then size is just the number of bytes to write in, and data is the data you are putting into the buffer, the new data. So this is what we need to use. Now, this, I guess I'll just have to show you, but we still have to use GL buffer data because this is what actually creates our buffer. GL buffer subdata just operates on an existing block allocated by GL buffer data. And furthermore, because of that, our buffer subdata function can't specify usage. Usage is specified when the block is created and can't be modified thereafter. So we do still need this write method. There's nothing wrong with this. So I'll just leave that as protected for now. But what we will do is have a public method called update, which will take in the number of elements we're writing, the actual array, and then the offset into the existing block that we want to start replacing at. First thing we have to do is bind, and then we can call GL buffer subdata with our same target. The offset is going to be, this offset is in bytes, but the one we give will be in count, like number of elements. So we'll do offset times size of t. T is just the template parameter of our whole class. I'll get to that in a minute. The size will be the number of elements times the size of each element, and then just give the data itself. So we could make this could just copy this template thing right here and do that, and that'd be fine. But really, we don't want to do this because a buffer should only ever store one type of data, and it certainly shouldn't change the type of data that it stores throughout its lifetime. That should be something determined when you create the buffer. So we'll just add that as another sort of class template parameter here, and then get rid of these. If it wasn't clear, having both of these be separate template functions means that this T array here can be of a different type than this T array here, and it would work fine because it just operates in bytes. So that's not what we want. We want float buffers to stay as float buffers and uint buffers to stay as uint buffers. Okay, so let's see what we get when we compile this. Unfortunately, we get a whole bunch of errors, 41 errors. And this is just because we've sort of rearranged our buffer class here. We've added some template parameters, and so previous code that uses this is no longer valid. So we're going to have to go back and change this. So that's I would say the only real advantage of having usage be stored here and sort of allowing the potential to store different data types by keeping both of these as template functions and just leaving the actual class template the same, is that you don't have to go back and rewrite all this other stuff. But it's not the correct way to do it. That's something you would do if you're working on a legacy code base and you're making it more modern or something. But ours is small enough that it won't take too much trouble to just rewrite everything to conform to this. And also it's the correct way to do it. So we should do that. We'll just go through each of our buffer classes here and sort of fill these out. So our buffer specializations we should still be able to, the user should be able to control the usage of those. We don't want all vertex buffers to be dynamic or all to be static. I mean, clearly that wouldn't even work for just this case that we have already, because we want our dynamics render object buffer to be dynamic and our sprite groups render object buffer to be static. So we need to sort of take in that template parameter at this level as well, and then just pass it down to our buffer. And the type of all of our vertex buffers will be float. Now, if we compile this, I will actually, I mean, obviously I still have all these other errors that I haven't fixed, but I will have some new errors in our vertex buffer here, which is MID, identifier not found, not found, not found. Now, what's happening here is that we have sort of a partial specialization of our buffer class. Our vertex buffer class is a partial specialization of the parent, because the type of the parent is ultimately dependent on the type of the child, because we're taking in a template parameter here that is then used to specify the type of the parent. And I couldn't tell you like exactly why logically that has this effect, but that's what's happening. And what that means is that for whatever reason, the compiler can't deduce like which scope are these variables that we're using here, MID, right, that are fields of our parent. It can't deduce that those should be of our parent, but we can get around that by just specifying that by explicitly getting them with the this pointer, which remember is like the current object. So that'll work fine. So that's vertex buffer. Vertex array we'll have to modify as well. Even though this is not a buffer, it does store a buffer, so we still need to take in a GL-enum usage, and then just send that to our buffer here, and down here, make sure to store the correct type, and return the correct type. And I think that's all we have to do here, not much. Index buffer will be similar to our vertex buffer, except it stores uints instead of floats. And again, I like to just sort of copy the template parameters for the parent constructor here. And then, of course, we now have to put this everywhere. So this.count, this.write, this.id, all that should be good. Our last one is uniform buffer. Which also stores floats. Still have to put this in a couple places. Well, we don't actually need it for mslot because that's part of this class, not the parent class. And then replace the template list here. And there we go. So if I compile now, should have fixed a good number of these errors. Yeah. So we have just some remaining ones in render object, shader. Oh, I did actually forget here that the index buffer takes in a vertex array as part of its constructor. And now that vertex array is templated, we need to make this constructor also templated. So I'll call this not type name GL-enum, and then vertex array of that type. That should be all we need there. Then moving on to render object, we're going to need two GL-enums because a render object stores both a vertex array and an index buffer. Simple change. Okay. And then what else we got here? We have our shader. It's not happy with something. Yes, taking in a uniform buffer. I think that should be it for our graphics library at least. Let's go ahead and build once again. And you can see, yes, now we are just getting some, oh no, there's still some stuff in render, I guess. Yeah, okay, well, whatever. So these take in render objects. So we'll need two parameters, VA and IB. And I should probably come in here and, actually, I'm not even sure we need these two methods anymore. But whatever, I'll leave them for now. If we rebuild now, only errors we should be getting are in our engine classes. And it does look like it. Got a whole bunch more errors, 92 new errors. Let's start fixing those, but we're done with everything. Our graphics library. Okay, I'll just go down the list here. So our render object in our dynamic, we need to specify the usage for the vertex array and the index buffer. Vertex array obviously is going to be dynamic draw, but the index buffer, the indices are never going to change, so that's just going to be GL static draw. Then we have a bunch more stuff in our render, our engine render. One for uniform buffer there, and then yeah, a bunch of render object stuff. Okay. That may have been most of it. Let's go ahead and rebuild. I think all that's going to be left is our map data stuff. Oh no. Okay, so now that our these draw functions in our render here are templated, they can't be defined in an external file. That's not entirely true, but basically they can't be defined outside of the header file here. So we'll just have to move all of this into our header here. It's not a huge deal, but I don't know, it does make it sort of messy. You can just minimize stuff there with the little like widget. Okay, so that's both of our draw functions. Oh yeah, and now that we've moved this in here, oh man, this sucks. Gotta include sprite. Delete it from there. Object identifier. Yeah, because oh, what did I named the. That's interesting. I named the variables in the draw definition in the header differently than I named them in the implementation file. Just make sure that's obj. Okay, so that's all the render stuff. Now we just have our map pipeline. So nothing's actually, no graphic stuff is actually stored in the map, I don't think. So it's all going to be in the chunk and the sprite groups. So our light buffer for each chunk will be GL static draw. This is just set when we load our map and never altered again. Then in our sprite group, both of these will be GL static draw, because our map data is set once when we load it from here and never again, and then obviously our indices are also static. Okay, so that should be most of it. Still calling a bad method here. Right, we changed that to update. And actually, let me look at the let's look at the actual signature to make sure I'm getting this right. Okay, so we want buffer dot update. count will be the length of our vertex array, then our actual vertex array, and we want to overwrite the whole thing, so offset will be 0. Okay, now I seem to have messed a bunch of stuff up here. I think this is, oh, it's only in sprite group. Oh no, also in chunk. So whenever you like define a templated type like this, when you actually create it, like you have to use the same template parameters, otherwise it'll say, you know, these are different types, which they are. But I think in Java you can usually leave those out and the compiler will figure it out. Okay, so that's our chunk, and then in our sprite group we have both static and there we go. That was kind of a lot of work, but not too bad. And now we can actually handle our dynamic vertex data here. So next, we need to actually create this render object initially. We've done most of the work here, but we're still just setting it to null pointer. So when we what's this called? Constructor. When we call our constructor, we'll go ahead and set our state just to make sure it's valid, then update our vertices to match the current state, and then create our render object. Render object equals new. I'll just copy and paste this. Count is going to be floats per dynamic. The vertices will be vertices. Layout still using 221 for now. And then have these other values, the constants, indices per quad, vertices per quad, and offsets, which is S index offsets. Okay, so now we should have everything we need to actually get our dynamic drawing on the screen. Let's go ahead and compile one last time, just make sure. And then head over to our main file and set it up. I'll call this dynamic, just dynamic for now. So we need position, we need velocity, we need max speed, which I'll just set to 100. Well, we need to actually include it first. Okay, and then what else do we need? We need a map of states, which takes sprite pointers and the current state. So we will actually need a sprite pointer from our sprite bank here. So I'll just go ahead and create one. I'll call it dsprite or dynamic sprite. Just create it if it doesn't exist. Test.bmp to 500, and this might just be the one. Yeah, that's the one we're already using. That's what already exists. And then we can define a map like inline here with this cool syntax. I'll just call our only state idle. It doesn't matter what it's called. And then there we go. So we create a map with a single state, idle, mapping it to our sprite here, and then set the current state to that state. Now in our draw loop here, I'll just go ahead and do this after I draw the map. We want to set our dynamics velocity, so we want to be able to move around with the WASD keys. Then we want to update our dynamics position based on that velocity, and then finally, once that's all done, we want to draw. So we'll do setvel of offset times negative dynamic get speed. I'll explain that in a bit. We want dynamic.update on our current frame delta, and then finally draw with our renderer. Let's just run this and see what we get. have a crash. Im render object was null pointer. Oh, of course it was. I don't know why I updated the vertices in here. That was dumb. It doesn't actually matter if we like create vertex data, because our vertices array is just initialized to all zeros at this point, so our render object will just store all zeros. But that's fine, because every frame, like before we even draw, we're updating, which then like sets the actual correct vertex data. So yeah, you shouldn't be updating vertices in the constructor. I don't know why I had that. So there we go. We now have a player. It is kind of moving, but the speed is all off. That's because the camera's moving faster than the player. It's kind of ugly. Let me change that. I'll just set this camera speed to the same as our dynamic speed, just 100 for now. And now we should get the camera perfectly tracking our dynamic. Huh, it's not. Frustrating. I think I've just done something a bit weird with the frame delta here. Oh yeah. Okay, that's dumb. So our offset is actually being modified here by camera speed, but also frame delta. And then we're setting our velocity to that, which has already been multiplied by frame delta, and then multiplying it by frame delta again. So our dynamic is moving way slower than it should. So we'll just take that out. We do want to leave this though, because we want like that sort of normalization there to stay the same for the camera and the player. But in our camera here, we'll just set offset times cam speed times render dot get frame delta. Just set it there directly, and then we have like the unmodified offset value for our dynamic. There we go. We have a dynamic. Our camera follows it around the screen, and it's very obvious, very clear to see that our dynamic is actually moving relative to the rest of the world, which is cool. So just quickly, why I set this to times negative dynamic dot get speed. And why that actually worked, I may not have shown that, but I added this operator minus to, oh no, never mind. I'm thinking down the line. So the reason this works is that our offset here is set up so that it's sort of like inverse of what you'd actually want. Because remember that positive y is up and positive x is to the right. But we have it so that when you press A, which is the left key, that gives you the positive value. So pressing A will move to the right, and pressing D will move to the left. And similarly, pressing S will move up, and pressing W will move down. Now this makes sense for our camera, because the way our camera works is that offset is applied to everything else. And so you sort of want the like inverse directions there. But with our dynamic, obviously we want to move that at intuitively. We want W to be up, S to be down. So I can just show you there. If I take that negative out, it'll sort of move the opposite direction of the camera, which is not what we want. So that is confusing and it's a bit messy right now, but that's why I did it. Okay. So we still, we have like the same problem we always have, which is this works great for the case where we have one thing, but what if we have 100 things or 1,000,000 things that we all need to, set velocity, update, and draw each frame? We have 100 different dynamics. We need some system to do this. Now, there's also an issue, which is another issue, which you haven't seen yet. But if I create another dynamic here, I'll just call it box, and I'll set it to be, somewhere in our world. I'll put it at like -100, -100, just so it's kind of out of the way. And I'll do the same thing, box.update. We don't want this one to move, so we won't set its velocity, but we do have to update and draw it. can see some interesting interaction here, where the order that they are drawn is entirely arbitrary. You can see my player that's moving around always gets drawn under this box. And when I say arbitrary, I don't mean chosen by the computer. I mean chosen by us, but still chosen arbitrarily. In this case, I've chosen to draw the box after the dynamic, after the player. But if instead I move that up, the box will get drawn first, and then the player will get drawn on top of that. So you can see here I sort of have the opposite effect of what it was last time, where now I, the player, am covering up the box. And this can be fine. Like this might not even be a problem that you would encounter in your game. Like say all of your dynamics are totally completely rigid and they have hitboxes that surround their entire like graphical space on the screen, then there would never even be any intersection anyway. So you don't have to worry about draw order. But there is another case that I want to account for, which is, say we have some object like this, like maybe it's a character, it's like a person who's sort of tall, and the effect we want, I don't really know how to describe this, but basically what we want to happen is if we, the player, are up here, it would look kind of awkward if when we just reached their head, the player stopped being able to walk, because the player's feet are right here, and they're somehow intersecting with this other character's head. Which, in the context of like realizing that this is all just a 2D plane, that makes sense. But for sort of top-down RPG games, almost all the time they use this like sort of fake isomorphic, like 2.5D, where the camera is not strictly top-down, it's like up and then sort of rotated at about a 45-degree angle on the world. And what that means is that stuff like this will look weird. And the way to make it not look weird is to allow the player to move down a little bit into this character's sprite so that their feet line up with like a believable position on the ground where they would be, like walking into this other character. So say that our I don't know how to draw this, but like our ground is like here. Then if we have this line where they intersect, then like obviously for a blue rectangle for our player, this would be their feet. And then for our character here in the sort of fake like 2.5 dimensions, that would be somewhere along their torso. So like at this point, it looks a lot more believable that the player can't walk any further. And what you need to do for that is actually have a hitbox that is somewhat, I don't want to say detached, but it doesn't take up the whole sprite. So the hitbox would be like this, that the player can walk slightly down into this character, but still stop at some point, not be able to just pass completely through them, like that. And obviously in this case, this is one of two cases we have. You would want the character, this blue rectangle, to be drawn after or behind the character that they are behind, because otherwise it wouldn't make any sense. You'd be like, the player would be here and they'd be like standing on this character's face, which would just, it's not what it should be. So that's one case. Then we have the other case, which is very similar, but sort of just the opposite, where we're coming at them from the other side. So in this case, we could, do the same thing again, where our player's head is intersecting with their feet, but that's not good. And now I said this is a different case. It's not really. I'm sort of thinking of it as a different case because in these examples, for like simplicity, I'm assuming that only the player is allowed to move. And this thing, like, it is dynamic so that you interact with it. It's like a rigid thing, but it doesn't move. So in this case, it's sort of the reverse of what we had already. And what we should be able to do is move up just like this so that our player's head, again, is like sort of near where their torso is. So it looks like they're actually looking eye to eye from our camera's perspective. And this would be achieved with the opposite effect, where remember this sort of stationary character has a hitbox right there, and now our player character would need to have a hitbox right here. And obviously this is sort of a weird shape, but you get the idea that we want these hitboxes to interact normally, but in a way that is not directly tied to the dimensions of our sprite. And that's like the main reason that we should be considering draw order here, because in cases like that, draw order needs to be correct, otherwise it'll just look totally weird, like it won't work at all. So there are a few ways to handle this. Like, again, for some games, it might work to not handle it at all. Dynamics are just stored in a vector, and the order that they're added to the vector is the order that they're drawn. But the way we're going to be doing it is draw them in an order determined by their position on screen. Because going back to this example, well, the first example, the player was up here trying to walk down into this other character, and we wanted the player to be drawn behind that other character. But now, when the player is below that other character on the screen, they are sort of in front of that character relative to our camera. Like, this orange hitbox part of this character is occluded by our player. That should no longer be drawn. So the order that our things are drawn in has to change based on how they move around, which is very tricky. It's not just a simple thing of like saying, oh, well, this is in the foreground, this is in the background. No, it has to change. So for this simple case, for 2D games, like higher up on the screen, so higher Y coordinates like towards the top of your screen, are usually considered to be further from the camera than those that are, near the bottom. So near the bottom is like very close. In the middle is sort of the center where the action is, like the point, the focal point, and then at the top is stuff that's like further away. But again, all of this is like fake. It's not actually scaled. There's no perspective going on. It's just sort of like your eyes perceive it that way, and it sort of looks weird if you don't properly account for that. But you could change this order as well. Like if you wanted your camera to be sort of looking at the scene from the other direction, you could have it so that things further down on the screen are further from the screen. I guess a good way to draw this would be the example I just described here. The camera's down here, but you could also have it where the camera's up here, or the camera's over here, or the camera's over here, or you could do some weird stuff somewhere else if you wanted like a true 2.5D sort of weird angled camera. I don't know how to do that. But yeah, you can just set your, like, imagine your camera being in different places and use that to order the way things are drawn differently. So that's what we're going to do. And for mine, we're just going to assume that the camera is actually down here, because that's where it usually is. But as we'll see, sort of, in quotes, moving your camera to a different part of the screen, or moving the way that it's looking, is very simple. It's just like a single line within our shaders. Okay, so within this method, we have two more options. The first option is to store our dynamics in some data structure, right? They have to be all grouped together. That's like the main thing that we need no matter what. Like, at least we need a vector here to store everything, because this is not going to work, drawing everything by hand. But yeah, so we could have some data structure that like physically rearranges the order of dynamics based on their relative coordinates. So going back to this example, say that I have two dynamics as I do here, and I'll draw them the same color. So these are like nodes sort of within a linked list. And in the first example, well, actually, no, in this example, where my stationary box is right here, sort of behind the blue player box, this should get drawn first, because then when this blue player box blue player box is drawn, that'll be drawn on top of the other one, so it'll overwrite what's there. So this would be the order there. But now, if my player moves to where it was up here in the first example, sort of behind the stationary one, then this needs to rearrange. The ordering is now incorrect. And it should be the other way around, where the player box is drawn first, and that now points to the stationary box, which would be drawn second and overwriting whatever part of the character it's drawn on top of. So that's one option. It's a naive implementation, though, for two reasons. First reason is it basically operates on the assumption that the only determining factor of what pixels are actually drawn, like what ends up in the final image that is drawn on our screen, is the order in which these things are drawn, which is not true. Obviously, that is part of it. As you saw here, when I reversed the order, like this being drawn first means that whatever is drawn after it, it will be drawn on top of that and overwrite that. But there is a better way to do this, which I'll talk about in a minute. So that assumption is false. And secondly, and the sort of main reason this is bad, is that it still gives us our current limitation that we have that we really, really want to get away from, which is that each of our dynamics is its own object and requires its own draw call. Because in this case, when ordering is important, each thing needs to be drawn in sequential order in order to get the correct final image, which is very bad. So I think at this point, like I say, that's very bad. For simple 2D stuff, it's not impractical. It will work, but it's certainly not correct. And it's actually the system I first implemented in like my work in progress 2D game engine, and it works just fine. Like it does work. It's not too terribly slow, but it does prevent batching, and it is more overhead than you need, certainly. So we will be opting for like the better architectural way to do this. So that's our first option, is sort of this structure, which, as I said, will work, but not as fast as it should be. The second option is a lot more complicated, which is why it's fun, because this is one we're going to be doing. So we're going to store our dynamics in some data structure, some grouping, some collection, but the order that it stores them in is not important. It's just sort of arbitrary. Like it's the order that they were added in to some degree, a mix of that and some other stuff, but it doesn't matter. The data structure will contain three main things. First is a list of the actual dynamics, like the stuff it contains that it needs to draw. A global quotes vertex array that stores all of the vertex data of all of the dynamics that it contains, which is immediately like a huge step up from what we have now, where each dynamic stores its own vertex array. And the last thing it'll store is a list of some other type of object that is used sort of like a sprite group to group stuff together into like chunks that are drawable with a single draw call. So essentially a sprite group for dynamics. So it'll draw dynamics into batches. And so this sort of main data structure will contain a vertex array with all the vertex data, but then each group will contain its own index buffer with indices into that global vertex array. So let me sort of draw out a little diagram here, because that's a lot of words and words aren't very helpful. Okay, so we'll have two structures here. For now, I'll just call them list and group. They're sort of connected in some interesting ways. So our list, first of all, contains some array of our dynamics. It's definitely how you spell dynamic. It also contains a vertex array with all of the vertex data of all of those dynamics. Then it has a list of this other type of groups. Now our group stores a list of uints. And these uints are indices into this list structure's actual list of dynamics. And our group will use that list of indices to then calculate some vertex indices to store in its own vertex buffer. So these two sort of connected, and then the index buffer obviously will be indices into the list's vertex array. Now, the last thing the group is going to store is a uint, which is its own index in the list's array of groups. And then obviously, I guess, just for completeness, one last arrow here. The list class actually also references the group class. So they're very interconnected. So I think I'll talk about some like common functions with these, and then we'll implement just a simple base class for them, and then I think we'll call it here. Because I don't want to sort of overwhelm you with all this like theory and then dive right into it and get, a third of the way through it. So we'll just get through the theory, like the structure of everything now, and then next time we'll actually start implementing this. So a bit more about like why these are sort of connected the way they are, is that time efficiency is the most important thing, of course. And so additional constraints on our data structure, other than it just needs to store a list of dynamics. Those dynamics should be drawn in a batched fashion, and they should be drawn in the correct order based on their position on the screen. In addition to all of that, which is already like a good number of constraints, we need order one insert, order one remove, and order one update for any dynamic in the list. Because, say our player shoots a bow and arrow, and that spawns an arrow, which is another dynamic. That needs to be able to be added to the list very quickly. That should be a constant time operation. Same thing for when it's removed. When that arrow hits an enemy, that arrow dynamic will despawn and needs to be able to be removed from the list very quickly. So yeah, those are some like more technical constraints on this. Now let's go through one scenario here, just sort of like a flow chart of what happens when we want to add to our list. So we want to add a new dynamic to this whole structure. Add. So we take some dynamic. We have a dynamic. And it needs to get properly inserted to both these structures and also the OpenGL like things that they wrap. So first of all, this is going to get inserted into our list. That's sort of the main like overall structure. Even though these both like kind of reference each other, list is the main one that the user will be interfacing with, and group is just sort of a helper class. So the list, it contains all this stuff. But what we're interested in right now is its dynamic list. So it has some, existing array of dynamics in memory, and that has, stuff ... and then we want to insert our new dynamic at some point in that array. And we will need these indices. So I'll label this one as I-1, this one is I, and this one is I+1. Okay, so now we at least have it stored in our list. But within that list, in order to actually get drawn, like that will just store vertex array data. Index buffer data is what is actually used to draw stuff. So we now need to add our dynamic to a group within our list so that there's index data generated for it in the index buffer and it will actually get drawn. So that's the next step, is we will take this I, this index in our dynamic array here that we inserted, and as you can see here, the group's uint array references that list. So we're going to be putting this in some group. its uint array of data. And that similarly, somewhere in memory, ... we will store this index I. Now, this group, this uint array, has its own indices that we're interested in. I'll call these j, so this will be j minus 1. This one that we just inserted to will be j, and this will be j plus 1. And the reason this is important is because our groups will only store a number of dynamics up to get max texture units, the maximum number of textures that we can draw, that we can bind at a single time, because that's essentially the only bottleneck to draw calls, which is the exact same way that our sprite group works. It works, it stores stuff up to get max sprite count. So our dynamic group will have to work the same way. So what this new J index represents is the texture index that this added dynamic will be drawn with. So we have a dynamic, we add it to our list at some index I. That index I is then moved into a group, copied into a group, where it is stored at another index j, and that index j is what we need to store in our vertex data. In this I, in our I-text index, this, our vertex data, needs to reflect our dynamics position in this group. Okay, so sort of extrapolating from that, we can draw up here. We have our lists vertex array there. And this also has some stuff in memory. But we will now add our x, y, st for our new dynamic, as well as j, this other index that we've gotten from our group. So x, y, st, our coordinate pair, our texture coordinate pair, and then our texture index. And then, of course, each dynamic will have, 4 actual vertices, but I don't want to write all those out. So the dynamic is also used, it sort of flows into this vertex array there. And now one last thing is, like I was saying, in order to actually draw this stuff, it needs to be contained in an index buffer. The last step, our group's index buffer. It has some data here, and then it'll contain some form of this basic pattern that we've used. 0, 1, 2, 0, 2, 3, obviously offset by the actual, sort of like multiplied by the actual index of our dynamic within the vertex array. So this I will further flow here. So yeah, that's hopefully that sort of makes sense. I think this visual thing, like, it helped me when I was designing this. And it might be the kind of thing that, like, it won't make sense to you actually see it in code, but I just think that showing you what we're actually going to do up front could be helpful there. Okay, so we'll leave that. I'll probably just do a quick recap of that next time when we start. But we can actually do sort of a little bit of groundwork up front here. I'll add a new class in our dynamic folder here called an indexed list. So this will be a base class for both our list structure and our group structure. You may have noticed, if you're especially sharp, that both of these data structures have quite a bit of base functionality in common. Both of them are like arrays of structures that we need to be able to add to and remove from in constant time, order 1. But they're also arrays in which the index of any given element must remain constant. We have to be able to add and remove in constant time, but we cannot change the order because each of these references the other. Our group stores a list of uints into this dynamic array. So if we shift stuff around here, this is going to be all messed up. And it also stores an index into our list's group array. So if we add a bunch of dynamics or remove a bunch of dynamics and we have to delete or add some new groups, this index will also get messed up. So we need to be able to add and remove in constant time, but not change the ordering. So that's like a good chunk of common functionality already. So we're going to create sort of a base class here. And this might be something that like it's like pretty general functionality, I think. So it might be better to put this in like the math library or whatever, but I've just put it in here. So I'll call this an indexed list. And we'll start with, I'm not going to make it private, I'm going to make it protected because we're going to inherit from it. So I'll have an imCount, which is the number of elements. And then an imNext, which is the next index to insert at. But also, I'll have a vector of uint, imopenings. And when we remove an element from an indexed list, we will add the index of the element that we removed to this imopenings list, so that like we free up that space, like our structure knows that that spot is free, but we don't have to shift anything around in order to free that up. We just have a list storing all the spots that are open. And then we will have an actual list of stuff. So sort of building on that idea of openings, we'll have this next index function, which will return the next, like the index to add to. And we'll start with just imNext. So imNext will sort of be like the end of our list, like the last spot, or the spot just past the last spot that we inserted. But again, we're not going to change any of this when stuff opens up. We're just going to store that in the array. So we'll start by default at that last spot, like the next spot to insert. But if we have values in our imopenings array, we want to use that. So we'll take it. We'll get the value, remove the value, and then return the index. And that should be .empty. So if there are openings, we'll use the next opening. Otherwise, we'll just insert at the next empty index. Okay. Now I can do the constructors. So count will just be the total number of slots that we have. And then we'll go ahead and reserve that number of slots in our vector here. Just so that if we're changing stuff around a lot, if we're deleting a lot, then this doesn't have to like resize and copy a bunch. We'll just reserve the maximum number of things that could possibly be added to that vector. We'll just reserve all that up front, so we never have to resize. That's sort of a minor optimization, but delete both of those. We'll have a virtual destructor, as we will be inheriting from this, or we'll just delete our list. Okay, so we'll have a bunch of simple methods here. Max size, which will return imCount. And we want get size, return the total number of elements currently contained, which will be the imNext, so the index of the last element we added, minus imopenings.size. So where we're up to adding contiguously minus the number of elements we've removed. We'll also just have get last, which will return imNext. Bool is empty. So our structure is empty if the size of our openings array, so the number of elements we've removed, is equal to the number of elements we've added. It's not as simple as just saying if mNext equals 0, because we could add one element, then remove it, and we're empty, but mNext will still be 1, so this would return false. So this is the correct way to do that. And then similarly is full. It's full if mNext is equal to mCount. So we've added stuff all the way up to the end of the array, and we have no openings. Okay. We'll have 3 more complex functions here, and then I think we'll call it for today. So our add method, if our structure is full, then we're just going to do nothing. Can't do anything. So we'll just print an error and return. And this will return the index at which this element was added to. So returning mCount. mCount is the length of our list here, created in our constructor, new t count. So mCount is like the first invalid index. It's like 1 greater than the length of the array. We'll get the next index we want to add at. Set our list at I equal to that. Set our list at the next index equal to the element we're taking in. And then we need to increment mNext, but only if we added to the end of the array. If next index returned an element from our openings list, then we're not going to increment mNext because we haven't added to the end of the array, so the mNext is the same. We'll just do mNext plus equals I equals mNext. Because if next index returns mNext, then it means that we didn't pop anything from the openings array, so we have added to the end, and then we need to move that end by 1. We need to increment it by 1. And then we'll just finally return the index. That's add. Then we have remove. So if I is greater than mCount, it's outside the bounds of our array. So it's an invalid index. And we'll return. Otherwise, we will just mark the current spot as open by adding this index to our list of openings. And finally, we will overload the array access operator to get an element at this index. And for now, we'll just assume that this is a valid index, but this is clearly a problem with our implementation that we'll have to adjust next time. Okay, and there we go. This probably doesn't compile. It might, I'm not sure. As I said, we're going to have to make some changes to it. Okay, good. So it does compile. So this indexed list, again, is just sort of the base functionality of both our list type and our group type here. The constraints, once again, are we need order 1, add, remove, and update. Update meaning like access. As well as order must stay the same. There's probably a specific word for that, but order must stay the same. When we remove something, it can't shuffle the elements around. When we add something, it can't shuffle the elements around because everything is linked together just using indices. And so those indices must remain constant. So yeah, this is sort of like a good chunk of the functionality for that. So next time we will work on this a bit more. We still have some more to do, and then start inheriting from it for our list and group classes. We might get through our whole dynamics thing. Probably not. Maybe. I'm not sure. It depends on how much extra explaining and retreading I do. But yeah, hopefully this was interesting. Hopefully you thought it was sort of cool that we now have the ability to get stuff moving around on the screen, even though it's super hacky and everything is drawn one by one in our main file here. I still think it's nice to see the actual end result up front. Well, to some degree the end result. The main functionality is there. It moves around the screen. It actually moves, and it updates everything. So yeah, hopefully you thought that was cool, and I'm looking forward to seeing you next time.